Hey Randy, how you doing? This is Chris. I'm going to go ahead and start the review for chemistry for you. So let's just go ahead and just do a couple of fundamental stuff real quick. Make sure we're good to go. I won't go ahead and belabor some of the finer points, and we'll just shoot for high yield information at this time. Sorry, I'm at the commons of the college, so there's probably going to be some noise as people are coming in and out and talking and whatnot. I do have the headphones in, so hopefully this sound quality be good for you. Okay, so let's just go ahead and review just a couple of the basic things. So we know that atoms, and again, I'm not going to talk about all the history and all that because as you and I talked about, we're going for the high yield information that you need to be relevant for what you're doing. So let's just make sure we're good with the atom, with the fundamental constituents of the atom. The atom is a fundamental unit of matter. Matter being something that has a certain mass and occupies a certain amount of volume. And we know that these atoms contain basically three fundamental components as far as chemistry is concerned for the most part. So in the nucleus, we have positively charged particles with a large amount of mass, and these positively charged particles are called protons. And then we have neutral. These are particles with no charge, and we call these neutrons. And both protons and neutrons have about the same mass, and we'll just say that these take up 1 AMU, or 1 atomic mass unit. Okay, and then in what we call orbitals, around the nucleus, we have very tiny, very low mass particles with negative charge. Okay, and of course we call those electrons. And we should say that the electrons don't orbit the atom like a planet orbits the sun, but rather because these electrons have wave-like characteristics, they inhabit an area or a volume around the nucleus and a cloud of probability where it's more likely to find it in a certain area than another area, and we call that cloud of probability an orbital. And these orbitals can have different energy levels depending on the atom and what we're talking about, and we'll kind of get to that. So those are the basic constituents of the atom. And we know that the basic force that holds an atom together is the electromagnetic force, and that can be written as the force between two charged objects just equals a constant we'll call K, and that's multiplied by Q, that's the charge on one object, times the charge on the other object divided by the distance between those two objects squared. And this classically, of course, is known as Coulomb's law, the law of electrostatics. So if I have a positively charged proton and a negatively charged electron, okay, we know that opposites in nature attract, so there will be an attractive force that wants to hold these together, and that force is related to the amount of charge that you have in the nucleus and, of course, the charge on the electron. And we say that every proton has 1 unit of fundamental charge. So every proton has 1 unit of charge, and we call that positive charge. And every electron has 1 unit. The same unit, the sign changes, and it's negative charge. So if I have a nucleus that has 3 charge, so 3 protons in it, and let's just say I have 1 electron here, then the force that this electron feels, plugging that into Coulomb's law, one of these is going to have more positives. Okay, so I'm just going to put a 3 fundamental units and 1, and then r squared. So depending on how close the electron is to the nucleus, and we know that some atoms are really big and some electrons may be much further away from the nucleus, so they're going to feel much less electrical force, electromagnetic interactive force. So that's the basic idea behind what holds an atom together. Okay, so let's go ahead and talk about how the electrons are arranged in atoms. And the electrons, like I said, are arranged in energy levels. Okay, energy levels. So if I have the nucleus here, kind of a way of imagining it is, okay, so I have a nucleus, and then in very discrete energy levels. So the electrons can only take very specific levels of energy, and this is part of the quantum nature of things. So you can imagine them like little planets orbiting, even though they're not, but this just makes it simple. The closest energy level, or the lowest energy, where an electron is the closest to the nucleus, is what we call the ground state. And we'll just say that this is n equals 1. So that's the first energy level. And then I can have other energy levels as well, depending on the atom and where those electrons are. And so maybe this is n equals 2. Now, because of the quantum nature of atoms, an electron can be in this energy level or this energy level, but it can't be in an energy level in between. It is quantized, and they're locked in very specific energy levels. And the reason that we know this is I can take this atom, I can excite it, and I can bump that, I can give this electron here enough energy to go up to the next energy level, okay, from 1 to 2. And then when that electron moves back down, okay, it'll move back down to the ground state. It has to release that exact amount of energy between those levels, and that energy is released in the form of light. Okay, and we can see that in what's called the spectra. Okay, the emission spectra of an atom. And if I take, let's just say I take a cathode ray tube, okay, and I put an electrical potential across that, and let's say this is full of hydrogen here, and I excite that hydrogen, so I have H2 hydrogen molecules in there. I'm going to excite the electrons in those hydrogen atoms. Those electrons are going to go move to higher energy levels, and then they're going to release light, and I'm going to see this thing glow here. And what I can do is I can take the light that is coming from that, and I can put that light through a prism, and what will happen is that light will then break up into its individual wavelengths, and I'll see something, in the case of hydrogen, I'll see something like this. If let's say this is red here, and this is blue here. What will happen is, when I break that light up through a prism, I'll see a really sharp red line, and then I'll see 3 distinct blue lines over here. And we know that as far as light is concerned, the redder the light is, the lower the energy, the bluer, the higher the energy. So what the quantum theory predicts is that if you imagine that this is the n equals 1, okay, n equals 2, n equals 3, this is not to scale, n equals 4, n equals 5, and n equals 6. Okay, so what has happened is I have taken an electron, and I have, so my electron's down here, and I have bumped it up to n equals 6. We'll start there. And then as that electron goes back down, because electrons like to be at the lowest possible energy level, if the electron could, it would like to get back down to 1. And let's say that it were to go from 6 all the way down to 2. Okay, so that's a pretty big jump. That's a pretty big, a pretty large amount of energy. And that jump from that quantum leap, if you will, from 6 down to 2, that energy, the exact amount of energy that this electron has to give off in the form of light, just happens to correspond with a small wavelength line of light here. If I had an electron that went from 6 down to 3, that would be the energy for this here. And then from 6 to 4, that would be enough energy to make this line here. And then from 6 to 5 gives us the red light. So we can see through the emission spectrum of atoms. In this case, I talked about hydrogen, and this particular set of visible lines are what we call the Balmer series. Okay, you can look that up if you want. a Balmer series is visible lines. Every single atom, every single element has its own set of lines. And of course, this is a really handy lab test that we can do. We can look at light from unknown elements. We can look at lights from stars and things like that. We can put that light through prisms, and the prisms will break the light up into its spectrum, and then we can compare that to the spectrum of all the elements, and we can figure out what these objects, what elements these objects have in them. So that's handy, and it is a nice validation that the current theory that we use to understand chemistry is a functional theory. Okay, so that's where we're at there. So when we talk about atoms, let's just go ahead and talk about looking at the periodic table of elements. Periodic table of elements is a really handy way of arranging atoms according to their atomic mass. You start at the top with the lowest atomic mass, and then you work your way down. And the periodic table of elements is divided into horizontal rows called periods, okay, and then vertical columns called groups. Now here's a cool thing. If you look, you'll start at the top, the very first period, period 1, and then the next period is 2, and 3, and 4, and 5, and so on and so forth down to about 7. So what this means is that if I have an element up here in period 1, that element has one energy level. The electrons in that element only occupy one energy level. However, if I have an element down here in period 2, there are 2 energy levels that electrons can exist in. In period 3, there are 3 energy levels that we can deal with. And an energy level can be looked at as n equals 1. That's the very first, that's what we call the ground state. It's the lowest energy level in an atom. So maybe this is the nucleus here. It's the closest to the nucleus. And then up from there is n equals 2. So if I look at an element here that is in period 1, that element, all the electrons in that element would be here in the lowest energy level. But an element with element that was in period 2 here is going to have 2 levels of energy where those electrons would normally want to occupy, and 3 energy levels, 4 energy levels, and so on and so forth. Okay. Now within these individual energy levels, these general levels of energy, I have within these different what we call orbitals. Okay, atomic orbitals, and we'll talk about those in a little bit. Okay, so that's that. Now, the most important level of energy that we really care about for chemistry is the outermost level, is the highest energy level. So, for example, if I have an element, okay, here in the 4th energy level, that element has electrons, that atom has electrons that can occupy 4 levels of energy. In chemistry, I am most concerned with that 4th level of energy, that outer level of energy, electrons that exist in this outer level, because this is where chemical bonding is concerned. This is where our chemical bonding occurs in this outer energy level. And so important is this that we call this outer level of energy the valence shell. Okay, it is the most important part of chemistry for what we're talking about here, and we call that the valence shell. Okay, so going back to the periodic table of elements, the periods are horizontal. They tell us the number of energy levels in an atom, and I also have groups. These are the columns. Okay, and the group tells me how many electrons are in the valence shell. Okay, so how many electrons are in the valence shell, and how many total shells do I have? Okay, so that's what the periodic table of elements fundamentally tells me. So with that in mind, let's just go ahead and take a look at a periodic table here that I drew. Okay, so let me just kind of orient you real quick. So here are my periods, moving across here. Okay, so period 1, period 2, period 3, period 4, 5, 6, etc. Okay, these here are my groups. I have group 1, group 2, 3, 4, 5, 6, 7, and 8. And these all the elements in here are what I call the super sexy swingers, because they do really interesting things with their electrons. And this area in the middle is actually called the transition metals. And they're really unique, and we'll talk about them later, but I don't really include them as part of the fundamental background of looking at the periodic table, because the electrons can move around much easier in the atomic orbitals of these versus these guys here. So let's start at these guys here. Okay, so what is this telling me? This tells me that elements here at the top only have one energy level, okay? And the groups tell me how many electrons are in that energy level. So if I go here and I take a look at this H, this is hydrogen, okay? This tells me that hydrogen is in period 1, so hydrogen only has one energy level, and there's only one electron in that energy level, in the valence shell, the outer shell. Okay, that's what that tells me. And while we're on the subject, let's just make sure we're good with, when we look at the periodic table of elements, okay, so then I actually look at an individual element like hydrogen, there are a couple of numbers I want you to be familiar with. There's a whole integer value number, so we've got 1 there, and then there's 1.001. There's a decimal number here. This right here is the symbol. Okay, this is just the symbol that we use for the element. This just happens to be one for hydrogen. This right here is called the atomic number. Okay, the atomic number is like a fingerprint. Every element has its own fingerprint, and the atomic number tells us the number of protons in that element. And the number of protons by default tells us the number of electrons that that element will have in nature. So hydrogen has an atomic number 1. That means that it has 1 proton, and in nature that hydrogen will also have 1 electron. Okay, so the atomic number is very important. This is called the atomic mass, or the atomic weight, and this tells us the average weight of all the different types of hydrogen. And if you look at compare a proton to an electron, the proton has what we call 1 AMU, or atomic mass unit, okay, per proton, and neutrons as well. Neutrons have the same, almost the same exact mass as a proton. Actually, neutrons are a little more massive, but that really won't matter for this particular discussion here. Now, an electron, however, an electron has about 1/1800th the mass, okay, of a proton. So really it's negligible. The mass of electrons is negligible, and really the number of protons tells us what the overall mass of that element should be. Well, why do I have this 0.001 then? Shouldn't it just be 1? Well, maybe that 0.001 takes into account the mass of the electron, but the mass of the electron is 1/1800th. Okay, so we would actually need to add a few more zeros on the end of that. What this takes into consideration is something known as an isotope. Okay, an isotope is an element that has the same number of protons. Okay, because this is what makes hydrogen is the atomic number, that 1 proton. Okay, what isotopes are elements that have the same number of protons but different numbers of neutrons. So the most common form of hydrogen is hydrogen with 1 proton. Okay, that's the most common form, but there are 2 other forms of hydrogen that we run into. There's a form that has 1 proton and 1 neutron. That's what we call deuterium. And then there's even another type isotope of hydrogen that has 1 proton and 2 neutrons, and we call that tritium. And you are familiar with tritium, as you see tritium gun sights and tritium watches in that. And as you might guess, when I start putting lots of neutrons in there, some of these atoms can become unstable, and the nucleus may have a tendency to want to break down, okay, decay, and that's what we call radioactivity. That's one of the mechanisms for radioactive decay, is a nucleus breaking down and releasing energy. And in the case of tritium, Okay, in the case of tritium, we see that as visible light that glows as that isotope of hydrogen decays. So this mass number takes into consideration the isotopes of this. So as you can tell, most of the hydrogen that we run into is actually the traditional form, with only a very tiny fraction of the hydrogen actually being deuterium or tritium. Every element has different isotopes, but hydrogen's just the one that's the easiest to talk about. Okay, so we're good there. So let's go back to the periodic table of elements here. Okay, so let's start at hydrogen. Hydrogen has an atomic number of 1. Okay, and then moving along the first period, I go to helium. Helium has an atomic number of 2. Lithium has an atomic number of 3. Beryllium 4. Boron 5. Carbon 6. Nitrogen 7. Oxygen 8. Fluorine 9. And neon 10. Okay, so we'll talk about the first 10. Okay, so let's now talk about the electronic configuration, the electron configuration in the atom. Okay, so like we said, atoms are divided into different energy levels. So let's start here at hydrogen. So hydrogen has an atomic number of 1. It only has 1 energy level, and that energy level contains 1 electron. That's what that means. So if we were to imagine hydrogen, hydrogen has a proton, like so, and then orbiting in just 1 energy level in an orbital, I would have an electron. Okay? Now, if we move on to helium, helium is still in the first period, so it only has 1 energy level, but it has two protons, which means it has 2 electrons. So helium is going to look something like this, 2 protons. All right. And in the first energy level, I'm going to have 2 electrons. Okay, fair enough. However, let's move down to lithium. Lithium is in the second period, which means that there are 2 shells of energy associated with this and 3 electrons. So we look at lithium. Lithium has 3 protons, but it has 2 shells around it. Okay, so you might guess the first shell has its electrons, and then the third electron is out in that second shell. And the same with beryllium. Okay, it has an atomic number of 4, so we have 4 electrons we need to deal with. So 2 in that first shell, and then 2 in the second. And then boron would be 5 electrons that we got to worry about. So there are 2 in the first, and then 3 in the second, 6, 7, 8, 9, 10, all the way out. Okay, and then we move down to sodium. Okay, sodium is 11, magnesium's 12. Okay, well, sodium has 11 electrons, and those electrons are spread out between the 3 levels of energy. But the outer shell, the valence shell, because this is in group 1, has 1 electron. Okay, so that kind of brings us into talking about the electron configuration. And so, like I said, you have these shells. Okay, you have these shells, but within the shell, we have sublevels. Okay, we have these sublevels that are called orbitals. And orbitals are little areas of probability where electrons can exist. And you've talked about this, where you have an s orbital, which is kind of a spherical cloud. Then you have these, what are we called, p orbitals. Okay, that look kind of like dumbbells, and then you have these d orbitals, which can take on all kinds of strange shapes, and you even have f orbitals, which can take on even more bizarre shapes of probability. Okay, so the way that this works is as electrons fill in, as we fill up the atoms, the electrons. There are a couple of principles. Okay, we have something called the Aufbau principle. The Aufbau principle, and that is the filling up principle. Okay, so it means that we fill from low to high energy, okay? So when we start filling atoms, we fill from the lower energy, so you start at the first shell, you fill the first shell up, and then you work your way out to those outer higher energy shells, because electrons like to be at lower energy, okay? We also have something called Hund's rule, which I'll talk about a little bit more as we get into electron configuration. We have Hund's rule, okay? And this all relates to something known as the Pauli exclusion principle that says that particles called fermions, okay, these are basically particles that, like electrons, protons and neutrons that have mass and a certain type of spin in that, they cannot exist in the exact same quantum state, okay? If that was the case, if I could put all the electrons in the same quantum state, there would be no need for periods in periodic table elements, because I could just put every electron in the n equals 1 state. But due to the exclusion principle, once I fill up a certain state and I have no more quantum states to put those electrons in, I have to move to higher energy levels. So it is the Pauli exclusion principle that ultimately creates the periodicity of the periodic table of elements. Okay, so let's talk about this. So when we fill, okay, when we talk about electron configuration of elements, all the elements on this side of the table, and then helium. Helium's the only one on this side. So these guys here and this guy here has a valence, their valence electrons, their valence are in s orbitals. Okay, so we call these the s block elements because their outer electrons are in s orbitals. Okay, now all of these elements in here, in this area here, their valence electrons are in what we call p orbitals. Okay, that's what we call the p block. And then these guys here in the middle are what we call the d block. And then you have the two lines at the bottom, the lanthanides and the actinides, and they belong in the f block. Okay. So when I look at filling an element, when I look at electron configuration, let's just start at hydrogen, and I'll show you how this works. Okay. So when we look at orbitals, okay, we look at an orbital, a single orbital can only contain a maximum of 2 electrons, okay? Maximum of 2 electrons per orbital. Okay, so let's start at hydrogen. Hydrogen is in the first energy level, okay, because it is a group 1, first energy level. So hydrogen is in the first period, and the first period only contains 1 orbital, what we call an s orbital, okay? An s orbital. 1 orbital, that's it. So when I look at the electrons in hydrogen, what I can do is I can do the configuration starting at the Aufbau principle, filling up, and I can say that the electrons are in the 1s1. So that would be the electronic configuration for hydrogen, because I have one energy, the only electron that hydrogen has, okay, that 1 electron is in the first energy level and it's in the s orbital, okay? Now let's move on to helium. Helium has 2 electrons that we need to worry about. Remember what I said, I could put 2 electrons in a single orbital. So helium electron configuration would be 1s2, okay? So I have 2 electrons in an s orbital, and those are all in the first energy level, okay? So that's where we're at there. So now what I'm going to do is I have filled up the first period, okay? I have no more quantum, I I have no more space, nowhere else to put these electrons. I have no more quantum states to place electrons in. So now I have to move down to the second energy level. And if you look at this, the second energy level has elements that are both in the s block and the p block. Okay, so I have multiple orbitals that I'm dealing with here. So let's just talk about lithium. Lithium has 3 electrons. So what I have to do is I have to start and I have to fill up the first energy level, right? Okay, so I have 2 electrons that can go in the first energy level, and those 2 electrons can go in an s orbital. So lithium, we're going to start at 1s2. Okay, and then that last electron has to go in the second energy level. And the way energy levels work is you have to fill up your s orbitals first, okay, and then you fill up your p orbitals. And every energy level has an s and a p, and then as you get higher and higher in energy level, you have d orbitals and f orbitals, and more or less, there are some exceptions, but more or less, you start at s, you fill your s's, then you fill your p's, and then your d's, and then your f's, okay? Now, so what I need to do, so what I do with lithium is I fill my 1s orbital, and then I move to the second shell, and I have another s orbital. Every energy level has an s orbital, so I need to put 1 electron into that. So 1s2, 2s1 for a total of 3 electrons. If we move on to beryllium here, I have 4 electrons I need to worry about. So I fill up 1s2, 2s2. Okay, so now beryllium, it is full. The s orbital is full, but remember in the second energy level, okay, I have p orbitals. Okay, and the way p orbitals work is you actually have 3 types of p orbitals. Okay, so if we look at your p orbitals, you have the px orbital that looks kind of like this. It's aligned on the x-axis, so that's a px, and then I have a py aligned along the y-axis here, and then if you can imagine kind of something coming out of the paper, okay, so I'll draw the dotted line here. So this is coming out of the paper along what we call the z-axis, and that's the pz orbital. And each of these orbitals can hold 2 electrons. So 2 electrons can go here, 2 can go here, 2 can go here. So all 3 p orbitals can hold a maximum of 6 electrons. And wouldn't you guess, by looking at this, 1, 2, 3, 4, 5, I have 6 elements in my p block. That should come as no surprise, knowing what we know about p orbitals. Okay, so let's go ahead and move on to boron. Boron, okay, has 5 electrons. So boron down here. So we'll start 1s2, fill up my first shell. Now I'm in the second shell, 2s2. Okay, that's 4 electrons, 2p1. Okay. Then we'll go ahead and we'll move on to carbon here. Okay, carbon has an atomic number of 6, so I have 6 electrons, so that's 1s2, 2s2, 2p2. Okay, and then I'm going to move on to nitrogen, which is 7, that's 1s2, 2s2, 2p3, right? And then I'll move on to oxygen, 1s2, 2s2, 2p4. Okay, and then I'll move on to fluorine, which is 1s2, 2s2, 2p5. And then finally I'm going to get to neon, which is 1s2, 2s2, 2p6. All right. How cool is that? So all of my p orbitals are filled, all of my s orbitals are filled. So then when I move down from neon, that energy level is completely full. Now I have to move down to my third energy level, and I start at sodium, and then sodium starts all over again. 1s, okay, so I have 11 electrons, so 1s2, 2s2, 2p6, and then let's just do sodium. What the heck, all right? So sodium is 1s2, 2s2, 2p6, and then 3s1, just like that, the Aufbau principle. Okay? Now, let's just talk a little bit about what we see happening here. So if you notice something interesting, if you notice all the elements on this right-hand side here, if we look at those elements, okay, so helium, neon, okay, and you also have argon, krypton, xenon, radon, okay. If you notice something about these guys here, their valence shell, their valence is full. Their valence shell is full, okay. So if you look at like fluorine here, okay, we look at fluorine, fluorine needs one electron. It just needs one electron, and its valence shell, okay, its outer shell, which is the second shell, would be completely full of electrons. You add one more electron, and now I have neon, which is a full valence. And here's an interesting thing. Remember when I said earlier that the valence shell determines chemical bonding, and it is the fact that you don't have a valence shell that leads to chemical bonding. So elements that don't have electrons, a full valence shell, are going to be chemically active. Elements that have a full valence shell, however, all of these guys here are not chemically active. They have no need to share or lose or gain electrons. They don't need to because their valence shell is full. And we call these guys over here the noble gases, okay, simply because they are noble. They are not particularly chemically active, okay? They don't react chemically or have significant chemical reactivity because their valence shell is full. The rest of these elements, however, have partially filled valence shells, which means that they're going to have more chemical activity. And that fundamentally is what makes all of chemistry work, is the fact that most elements do not have a full valence shell. I think I'm going to cut it off here, and then we'll pick it up in another video. All right, take it easy, Randy.